Hello everybody and welcome to this second part of the All-in Meta-Analysis webinar. My name is Peter Grimold. I am the group leader of the machine learning group at CWI in Amsterdam. I'm also full professor of statistics at Leiden University. I'm the supervisor of Judith, who has already told you a lot about All-in Meta-Analysis. Specifically, she has shown you some graphs which I think give a good idea of what it does in practice. So in the second part, I'm going to talk a bit more about the statistical background. How exactly is it defined? What does it do? How can we implement it? And how can it work? So all-in meta-analysis is part of a whole area, which also goes by the name of safe testing or always valid confidence sequences. And all these things have in common that they are about statistics where you can stop data assembling, stop gathering data at any time you like, and you can continue always if you like to do that. As you can see, recently there has been, very recently actually, there has been a big flurry of activity in the subject. Although the roots are quite old, it goes back to work by a famous mathematician, Robbins, from around 1970. This work inspired later work on group sequential testing and alpha spending. And it also inspired the current work, which, however, in its details is quite different. And the most important difference is that we can do statistics while never having to specify a maximum number of outcomes or never having to specify how often you can look at the data. So I am going to explain all these ideas using the simplest testing problem around, namely that of testing whether the mean of a normal distribution is 0 or not when the variance is given, the traditional z-test. But everything I'm going to say basically transfers to general testing problems. So this is just to give you the general idea. I stick to this very simple problem. We will also go to the log rank test later. So my null hypothesis says that the mean of a normal is 0. The alternative says that it's larger than 0. The traditional z-test just tells me to fix a sample size n and then reject if the z-score is larger than 1.645. Notice that we're doing a one-sided test here, so it's not 1.96. And n is here fixed in advance. Of course, if you want a certain power, you may have to use that to determine n, but you do that before you actually start gathering data. Now, in practice, we often have a minimum clinically relevant effect size. So, for example, the problem is only interesting if the mean is larger than some given mu larger than 0. In that case, we would still use the same test. But this second type of test can also be performed in a different way. We can also do a likelihood ratio test. So if you do a likelihood ratio test, we take the density of the data, the likelihood, according to the alternative distribution. So that's a normal with mean larger than mu. And then we typically take the one which is, in a way, the most pessimistic one, which is the closest to the null hypothesis. So we take the normal with mean actually equal to mu, not larger than mu. We divide it by the likelihood of the data according to a normal with mean 0. So phi is the standard density of a normal. And when we reject the null if the likelihood ratio is larger than some threshold. Now, by choosing the threshold carefully, we can actually make these two tests equivalent. Why is that so? Well, of course, rejecting the null if the likelihood is larger than something is equivalent to rejecting the null if the log likelihood is larger than something. And you can write the log likelihood as a sum of squared errors, which in itself is an increasing function of the average of the x values, which is just the maximum likelihood estimator. The z-score is also an increasing function of the likelihood of the average of the x values. So z larger than a certain value corresponds also to the likelihood larger than a certain value. So the test can be made equivalent. So traditionally, what one does if one does a z-test can be viewed as a likelihood ratio test, where you reject the null if the likelihood has a certain value, it's larger than something, which corresponds to z larger than 1.6. So we're going to do it differently in safe testing, or equivalently all-in meta-analysis. We don't have n fixed. We can basically stop whenever we like. But once we stop, we reject the null if the likelihood ratio that we observed is larger than 1 over alpha, where alpha is our significance level. And otherwise we accept. So notice that the threshold for us does not depend on the sample size n. Totally not. It only depends on alpha. It's basically always 1 over alpha. So I will use 20 as a running example, which is 1, because 1 over 20 is the conventional 0.05. Now, how does this compare? Well, if the alternative is true, and let's say that the data actually come from mu, then the likelihood ratio will be larger than 20 if, very roughly, z is larger than 2.4. So this test is a lot more conservative. So that seems a bad idea. We will typically end up just not rejecting the null, even if a classical test would. So why are we going to do this? Well, bear with me. So a famous result in probability theory is so-called Veal's inequality. And the Veal's inequality says that for every fixed level alpha, the probability that the likelihood ratio will ever exceed 1 over alpha is bounded by alpha. So in our case, the probability under the null hypothesis that the likelihood ratio will ever get larger than 20 is bounded by 0.05. So this may be a bit unusual for you. We have here a statement of a probability about something which involves potentially an infinite sequence of data. It doesn't say something for a fixed n. It says the probability that something will ever happen. That probability is smaller than 0.05. So if the null is true, then your likelihood ratio in all likelihood will never get larger than 20, no matter how long you sample. Because you have Veal's inequality, we can use our method. We reject if the likelihood is larger than 20 and have type 1 error guarantee, no matter when we stop. In fact, we can use the most aggressive stopping rule possible. We stop and reject as soon as the likelihood ratio is larger than 20. And otherwise, we keep on going until we run out of patience or money. So now the interesting thing comes, because if your data actually come from you, so the alternative is true and you would like to reject, and you want to get, say, 80% power, then you actually do need to reserve a bit more data with the safe test because it is more conservative. But on the other hand, because you can do optional stopping, in many cases you will actually stop earlier than the total amount you reserved. So if the alternative is true, it turns out that on average you need about as much data before you can reject a null as you would with the most powerful fixed sample size test. So in a fixed sample classical test, you fix n, it will have some value. Here you need to reserve for a larger n. So if n stands for patients, you might pay a bit more because you need more patients in the worst case. But on average, you need about the same if you stop as soon as the likelihood ratio is larger than 20. So you can get back a lot of what you lose by being more conservative because you can do optional stopping. So then why would you adopt such a safe testing or all-in approach? We can stop whenever we like. That's the big difference to the classical test. Now we need to prepare for a larger sample size. That's the bad news. But the good news is that in practice, we will often need less if we do optional stopping and we stop as soon as the likelihood ratio is large. And it may also be the case that we are lucky. If the effect is stronger than anticipated, so in our example, if the actual distribution is in the alternative and the effect is larger than mu, then we will need even less before we can reject. Also, if the result is promising but not conclusive, and we do happen to have a little bit more money, then we can add new data without any problems. And as we will see on the coming slides, we can also easily combine the data we already have with data coming, for example, from different studies, even if the decision to start those studies was based in part on previous data. So there are good reasons for doing this. So what happens if data come from different studies? Now we move from what is called safe testing to all-in meta-analysis. We have several trials, and they each may have different means. So what does that mean? Well, we still think that under the null hypothesis, the means are always 0. So the means would, for example, be the efficacy related to the efficacy of a certain pill. And the alternative might, of course, depend on the subpopulation you test. So in different hospitals, you have a different subpopulation, and the effect may be either stronger or weaker. So we may have different trials in different hospitals. They each got their own effect size. So we have different alternatives, but the null is always the same. Well, in this case, we can define a new likelihood ratio simply by multiplying out the likelihood ratios of all the individual tests. So how does this play out mathematically? For every individual test, you have a likelihood ratio, which is itself a product of normals. And now you multiply all these products again, where each trial has its own delta J. If we do this, then we still have the type 1 error guarantee because of Wills inequality, even though the trials may have different effect sizes, because if all the effect sizes are 0, if all the mu's are 0, then the probability that the product over all the trials will ever be larger than 20 is still smaller than 0.05. So we do have type 1 error guarantee. Now, in practice, we may not know what the individual deltas are, or we may think that some of the studies may be a bit too optimistic or a bit too pessimistic even. So we can also do something else. What we actually can do is use the same delta, the one which we think is the minimum interesting one, for all the trials. So we now have a multiplication of likelihood ratios, where each likelihood ratio has the same form. It's comparing a normal with mean delta to a normal with mean 0. And interestingly, it doesn't matter what delta we choose. No matter what delta we choose, our type 1 error guarantee is still valid. The probability that the product will ever go larger than 20, if the null is true, is smaller than 1 in 20. This holds for every delta we might want to choose, as long as we choose it before we actually see the data. But of course, we have to pick a clever delta. If we choose delta is 0, then the likelihood ratio is always 1. And then clearly it will never become larger than 20, but everything is useless. So what is a good choice for delta? Well, we want to have a choice so that if the alternative is true and useful for us, the likelihood ratio grows as fast as possible. So in this case, that would, for example, be the smallest delta that is still of interest, and that might often be the minimum of all the deltas involved. Another important thing to note here is that it is okay if some of the trials, if the decision to start some of the trials depends on outcomes or interim outcomes of other trials. This Wills inequality is not affected by that. So even if I start the 5th trial because the 4th trial had a certain promising result, everything still works. If the null is true, then the 4th trial having a significant result was a fluke. But even so, the probability that this product will ever get larger than 20 is smaller than 1 over 20. So there can be dependencies between tests, and we still have the type 1 error guarantee. Now, of course, what happens in practice, for example, in the BCG meta-analysis, is that data comes in sequentially and is interleaved. So we get data from different studies. At day 1, you get data from study 3. At day 2, you get data from study 5, etc. Well, that doesn't matter. Basically, the type 1 error guarantee will still hold. We can just multiply out all the likelihood ratios we've seen so far. So for every data point of every study, we divide phi delta between phi and by phi 0. We take the product so far. The probability that it will ever get larger than 20 and that we reject the null is bounded by 0.05. We have our type 1 error guarantee. And this holds, and now it gets really different from approaches like alpha spending. This even holds if we include new studies later on. So after the first 3 studies are finished, we might think, this looks so interesting, but we still don't know. Let's add a 4th study, and let's add it in some different country where they still have the stamina and the money to do it. It doesn't matter. We can still keep multiplying also with the new study results. The probability that we ever go beyond 20 remains bounded by 0.05. So now I come to the final part of this talk. How is all this even possible? And to explain that without going into too much mathematics, I can best give you the gambling interpretation of what we're doing here. So I'm now going to look at a slight modification of the testing problem we had so far. This is a testing problem where we go to a casino and we want to test whether the casino is really fair in the sense that the probability of red is exactly 1/2. So we assume a casino without a zero. So if the roulette wheel would be fair, probability would be really 1/2. For some reason, we think it might not be completely fair. Some things are a bit dodgy. Maybe we think that the alternative is that it's 1/3. Now, clearly, if the probability is 1/3, we can actually make money in this casino, right? We can gamble in a clever way and get rich. So now we're gonna gamble on the outcomes in a way so that we get rich as fast as possible if the alternative is true. How do we do this? Well, one way of doing it is as follows. Let's say we invest S dollars on the roulette table. So then we put 1/3 of our money on red and 2/3 on black. Now, then the roulette wheel is turned. And what is the payoff? So if the outcome is red, then of course we lose the part we put on black. So we lose 2/3 times S. And the 1/3 times S that we put on red gets now multiplied by 2, right? Because you get 2 times your money back in the casino if you put something on red. Now, and this is the crucial thing, note that 2/3 times S, which is what we get back, can be written as the probability of red according to the distribution with bias 1/3 divided by 1/2. It's multiplied 2, it's the same as divided by 1/2. So it's the probability of the outcome according to the alternative divided by probability according to 1/2, the probability of the outcome according to the null hypothesis. So it looks like a likelihood ratio. And the same thing holds if the actual outcome is black. Then we actually get more back than we invested rather than less, because we put more than half of our money on black. We get 4/3 our money back. And that can again be written as the probability of the outcome according to the alternative, which is 2/3 divided by the probability according to 1/2, which is 1/2. So in both cases, no matter what the outcome is, the payoff is what we invested, which is S times the likelihood ratio. And now we're going to keep on doing this. We start with an initial capital of S0. We put 1/3 on red and 2/3 on black. Now, after the first turn of the wheel, our final capital is the likelihood ratio times our initial capital. Now we reinvest. We reinvest everything in this game in the second round. Now the final outcome is what we invested in the second round times the likelihood ratio of the second round. And that is, of course, the same thing as what we reinvested in the beginning times the full likelihood ratio so far. And now we reinvest S2 again, and then we reinvest S3, and so on. So if you play this game repeatedly, let's say n times, and at day 1 you start with €1, then your final capital after n days and rounds is just the likelihood ratio of the two hypotheses. And clearly then, the higher the likelihood ratio, literally the more money you have gained, so the more evidence you have against the null hypothesis that the casino is fair. At the same time, if the null is true, if the casino is fair, you do not expect to gain any money, not using the strategy you used and not using any other strategy. And notably, this holds, as anybody who's ever been to the casino knows, no matter what your rule for stopping and going home is. So you might say, okay, I keep on gambling and reinvesting all my money on the roulette table until I've made $20, or it is 2022. That will not work. You can also say, okay, once I've seen 3 reds, I'm going to put more money on red. And if I've seen 7 reds, I'm going to put more money on black. It won't help. If the casino is fair, then you will not get rich. You never expect to gain any money. And if you work out the math, in particular, this means that the probability, no matter when you stop, no matter what strategies you use, every strategy corresponds to a likelihood ratio. And the probability that such a likelihood ratio ever gets larger than alpha, which means that you've made more, let's say that alpha is 20, more than €20, is smaller than 1 over 20. Now, I should add here that you might also want to think, for example, well, maybe some of the tables in this casino are unfair. So you might gamble a few times at table 1 and then take all your money and go to table 2 and gamble there. Well, if the null hypothesis is that they're all fair, then this won't help either. The probability that you will ever get more than $20 is still smaller than 1 in 20. No matter in what way you move from table to table, no matter what your strategy is for gambling. So this is why we can do meta-analysis with many different trials, we can also always go to a new table, which means doing a new trial. It is literally the same kind of game. Here I showed it to you for the real casino game where you gamble on red or black, but the same story holds for normal likelihood ratios. Basically, any statistical problem can be turned into a casino-like problem. You can turn it into bets where you don't expect to gain any money with these bets if the null hypothesis is true. We can also do this for log ranks based statistics, and that is what we do in the BCG meta-analysis. So you can think of that in two ways. You can look at the log rank statistic. I showed the formula here for every single event. So it's a one-shot log rank statistic. Think of that as a normally distributed random variable. It's not really normal, but we can act as if, and then use the test we've seen earlier where we use the normal likelihood ratio. That's one way of viewing it. Another way of viewing it is really more directly in terms of the casino story, because really this is a discrete problem. We have to gamble on whether the next event will be in the placebo group or in the treatment group. And what we do in the BCG trial is we have a betting strategy which makes us rich if there's at least 20% less COVID in the treatment group. So basically, as soon as there's an event in the treatment group, with our gambling strategy, we lose money. If there's an event in the control group, we win money. And under the null, with this strategy, we will not get rich. And if we get rich, we have evidence that the null is false, that the BCG vaccination helps. Now, something about terminology. In the papers we wrote on this, these individual chunks, individual bets are called e-values. The general story is that every e-value corresponds to a bet, which would not give you any money if the null would be true. And in simple cases, like the log rank case, the normal case, these bets also have the form of likelihood ratios. But in more complicated cases, which I won't talk about here, they have a more general form. The important thing is not that they are likelihood ratios, but they can be interpreted in terms of bets. So before I stop, a final note. Some of you might be familiar with Walt's sequential probability ratio test from the 1940s, and it looks very similar. In fact, it is only similar in relatively simple problems, like the ones we're looking at here. But in those simple problems, it might be nice to investigate the difference. So the SPRT says it's also sequential, the sample size is not fixed, and it says you should keep sampling until your likelihood ratio is larger than 1 minus beta over alpha, smaller than alpha over 1 minus beta, where 1 minus beta is the power which you have to set in advance. So it is sequential, but it has a fixed stopping rule. You really have to use the stopping rule to get power beta and type 1 error alpha. If you change the stopping rule, then it won't work anymore. In contrast, we can stop whenever we like, as I claimed multiple times. And once we stop, we reject if the likelihood ratio is larger than 1 over alpha. So the reason we get away with this is that we are slightly more conservative than Walt. So for example, if you have power 0.8, then if we stop, we reject if the likelihood ratio is larger than 20, whereas Walt would stop and reject as soon as the likelihood ratio is larger than 16. So we are a bit more conservative. In the worst case, again, we need a little bit more data than Walt, but not much actually. But there's a huge gain, right? The price is we might need a little bit more data than Walt, and the huge gain is that we keep the type 1 error, even if then we hear that there's a new study and we want to combine the results, or there's more data to continue our study. We can just keep multiplying all the results, and the type 1 error remains valid. So this brings me to the end of this webinar. And the take-home message is basically what I just repeated. By doing things based on a likelihood ratio, or more generally an e-value, where you reject if it's larger than 1 over alpha, you pay a price in the sense that in the worst case you need more data, but there's a huge gain, as I said multiple times, because you can always add new data. And in meta-analysis, this huge gain is of course essential, especially if we want to do it like we want to do in BCG. We want to do it interim. We want to keep on doing the meta-analysis as new data comes in. So that's it, and I look forward to discussing this with you further. Thank you.